Good morning, everybody. It's nice, or almost lunchtime, in fact. It's nice to be in front of a real audience again after so long time, and indeed in a few weeks in front of real students again. So indeed, I will talk about using plasma indeed for using the CO2 and converting it into useful chemicals. And I will show especially how we can improve the performance by modeling. Yeah, so this is just very quickly about the problems. We all know about the problems of global warming and our dependence on fossil fuels and the rising energy demands. Of course, there is a solution of renewable energy, but this also comes with its problems because of the peak powers. But then there is a solution if we can convert these greenhouse gases, CO2, but also methane, into new fuels or value-added chemicals, and we call these solar fuels. And it's even better if we can use plasma for this. Or more in general, if we can do electrification of chemical reactions. So it's not only CO2 conversion, but also methane conversion and nitrogen fixation, for instance. But of course, there is more research needed to understand the underlying mechanisms. And that is what we try to do by either computer modeling and also experiments. Now, maybe not all of you know what is a plasma. So plasma actually is a partially ionized gas. So it's also called the fourth state of matter. So if you have a solid, and you bring in energy, you get a liquid. If you then bring in more energy, you get a gas. And then if you bring in more energy, you get a plasma. So it's actually an ionized gas. So it means it has electrons and ions flying around next to neutral gas molecules. And the advantages are that especially the small electrons are heated by the applied electric field. So they are mostly heated, and they can activate the molecules, so they can dissociate inert molecules like CO2, but also methane and nitrogen. So, and that means that thermodynamically unfavorable reactions like CO2 dissociation can take place at ambient conditions. So you don't need to heat the entire gas. So the reactions can take place at ambient conditions of temperature and pressure. And a plasma is created, in this example, for instance, by bringing in a temperature, but it can also be by bringing in energy. This can also be electrical energy. So, and this can then also be renewable energy, renewable electricity, because a plasma can be very easily switched on and off. So it's actually very suitable to be combined with fluctuating renewable electricity. Now there exist different types of plasmas that can be used for CCU. One type is a dielectric barrier discharge. Another type is a microwave plasma. I will not go into detail because the time is of course very short. And another type is a gliding arc plasma. I just show you these examples because I come back to that later in the next slide. Because the next slide shows an overview. This is the state of the art of CO2 splitting that we did a couple of years ago, but actually it is still very up to date for different types of plasmas that we collected from literature. And we plot here the energy efficiency as a function of the conversion. And as you can see that for some types like microwave plasma, they can reach an energy efficiency of even up to 90%. But this was obtained at reduced pressure and very specific conditions of supersonic flow. So this was is not so easy to realize. On the other hand, there are gliding arc plasmas. So they are here, the gliding arc plasmas here. They are also above the efficiency target. So the green dashed curve is what we defined as the efficiency target, 60%, for plasma to be competitive with other emerging technologies and also with classical technologies. So, and it was also shown to be higher than the thermal equilibrium conversion. And then there is also dielectric barrier discharges that I also showed at a previous slide, but there the energy efficiency actually is far too low, a factor 4 too low, in fact, to be competitive. Now, this is the picture for pure CO2 conversion. We made a similar overview, but it's more busy, for dry reforming of methane. Here it's actually the same picture for DBD and also corona discharges, the famous corona. But here we plot the energy cost. The reason actually was that you can only define the exact energy efficiency of the process if you know all the products that are formed. And in CO2 splitting, this is easy. This is just CO and oxygen. In dry reforming, you can make syngas, but you can also make methanol, formaldehyde, and other products. So it's more difficult to define the exact energy efficiency. So we defined the energy cost, and the efficiency target was 4.3 electron volt per molecule. So again, this green dashed curve is the efficiency target. This was then specifically defined for syngas formation. So you see again that DBD, actually the energy cost, because now the y-axis is reversed. So the lower values means too high energy cost. So DBD gives again too high energy costs. Now this is specifically for syngas formation, but if a DBD actually is more easy to be combined with catalysts. And if you can find suitable catalysts that can then selectively form, for instance, methanol or other oxygenates that have a higher value, then the criterion is less strict. Then, for instance, the value-added product has a higher value, and then a higher energy cost can already make the process more competitive, because in another process you would need a second process, for instance, to process the syngas in Fischer-Tropsch to create the other products. But we also see that microwave plasma, so the red curve, the red points here, very striking. There are not so many data points in literature, and the energy cost seems to be very high. This is quite striking, because for CO2 splitting, these were the best results. On the other hand, for dry reforming, very good results have been obtained. So the blue data points here, again above the efficiency targets, and also above thermal equilibrium. And then there are also other types of plasmas, like APGD, that stands for atmospheric pressure glow discharges, and also nanosecond pulsed plasmas and spark discharges. These are other types of plasmas which seem also be very promising, but not so many data have been obtained yet in literature. So this was actually also in our review paper, but this also contains more data points because we made an update just last month, so it contains more recent data as well. Okay, so this was the state of the art. Then if we see what type of research we do in our group on CCU, we do experiments to improve the performance and also modeling to get a better understanding. On one hand, this includes the plasma chemistry. So this is for CO2, nitrogen, and methane. We focus on specifically the role of the vibrational levels, because it is, we found out that if the dissociation occurs through vibrational kinetics, this is the most efficient process. But we also look specifically at thermal conversion, because in many plasma types, it turns out to be quite thermal as well. But we also look at all combinations, as shown here. We also look at plasma catalysis, for instance, in packed bed plasma reactors, plasma catalysis reactors. We try to answer questions like, can plasma be formed in catalyst pores? And we also study the interaction of plasma species on catalyst surface by DFT calculations and also microkinetic modeling. And we also study plasma reactors in all types that I mentioned, DBD, packed bed DBD, microwave plasmas, gliding arc plasmas, and atmospheric pressure glow discharges. But I understood it's not the purpose of these talks to give an overview of the group, so I picked up one example, which is on plasma reactor design improvements. So here I show a gliding arc plasmatron that we have in the group. And actually you see here the design. So the reactor body is at cathode potential, and the anode, or the reactor outlet, is at anode. And you have tangential inlets. And if I show here, yeah, I didn't have the animations because I had to bring the presentation on stick. But actually, there are tangential inlets, and the gas flow pattern is an outer vortex. It's difficult to see here, but I don't know whether you see. There is an outer vortex, and then when the gas flows to the outer vortex, maybe I can show like this, it reaches the end of the reactor, and then it has lost some speed, so it has an inner vortex with a smaller radius, and then leaves the reactor through the outlets. Now the arc is formed and actually stabilized within around 1 millisecond and is confined by the flow in the center. And in the ideal case, the inner vortex flows exactly through the hot plasma in the center. So, so that there is efficient gas conversion. So that is the specific design of this gliding arc plasmatron. Now here is some results of this, and here you see an animation. So you see the gas flowing through the outer vortex and then in the inner vortex. So these are experimental data for different diameters of the outlet diameter. We see that the CO2 conversion in this case was around 1 to 9%, and the energy efficiency was typically around 35%. And the values were actually the best for the smallest anode diameter, so the black points. And that is actually because that is with the smallest anode diameter, because then the reverse vortex effect is the most pronounced. That is actually what we found out by modeling, and that was also backed up by experiments. This is a result in that same reactor for dry reforming, where we found that upon addition of nitrogen and oxygen, so we could mimic more real gas effluents, that the conversion was actually improved. So we see that the CO2 conversion was around 30 to 52%, and the methane conversion was up to 99%. And the energy cost was between 3.5 and 5 electron volt per molecule, or in kilojoule per liter between 12 and 20. So this is actually very competitive, because if you remember, in the state of the art, the efficiency target was defined as 4.3 electron volt per molecule. So we see that we are around that efficiency target in this case. And also we found that nitrogen actually helped to stabilize the plasma. So in many effluents there is a lot of nitrogen present. So this actually seems to be even beneficial. And also oxygen addition helps to improve the methane conversion, and only for higher oxygen fractions it did reduce the CO2 conversion to some extent. And the energy cost also was reduced upon oxygen addition. Then we saw that in the gliding arc plasmatron, the CO2 conversion in pure CO2 splitting was still quite limited. So we also built some reactor design improvements. This is a dual vortex plasmatron, where we have 2 symmetric outlet electrodes, not just 1, but 2. So that you have the discharge elongated in the 2 directions, as you can see here, in this and this. So this is just an artist view, of course, of the arc. And then there is a longer residence time and a higher conversion. And this shows the experimental results. So we see that the energy efficiency was between 35 and 40%, so a little bit higher than in the gliding arc plasmatron. And a conversion up to 9.5%. So actually it was not so much higher in practice, but we found that by computer simulations, that higher power and flow rate gave better results, but in practice we were limited because our power supply could not handle these higher powers. So in the past years, we were building a new power supply So this was a bit out of our, because we are chemists, so it was not so straightforward. But actually, we managed to build a power supply that is able to handle higher powers. And now we are about to test to see whether we are now able to reach higher powers for the same energy efficiency. And then the last example that I want to show is for an atmospheric pressure glow discharge, where I also want to show that based on modeling, we could predict design improvements. So for a basic design, and then we had another design which was based on a vortex flow, where we found that turbulence made that more gas could pass through the plasma. So there was a longer residence time of the gas through the plasma, which could also improve the conversion. And also because of the turbulence, there was more cooling so that we could use a higher power, and that could also improve the conversion. And then we also designed what we call a confined design so that all the gas could pass through the plasma. And the results are shown here. So for the CO2 conversion in the upper figure and the energy efficiency in the lower figure, with the basic design, we only had like 3 to 4% conversion. For the vortex design, it went up to 8%. So especially at the higher powers, it was a bit better. For the confined design, it was up to 12%. That is because more gas could pass through the plasma, which is indeed better. But there were more heat losses, and that's why the energy efficiency was a bit lower. But in general, the efficiency was up to 35%. So the efficiency was comparable, but at a higher energy conversion. And we are now looking also for further improvements, working more on the turbulence and the confinement, but then also less heat losses. And this is the last result, which is then we used this very recently, this confined APGD for dry reforming of methane, where we see that we reach CO2 conversions up to 64% and methane conversions up to 94%, and energy costs around 3.5 to 4 electron volt per molecule, which is then also below this energy costs. And this is a paper that we just submitted. So, and then just to summarize, I hope that I showed that plasma technology is very promising for CO2 conversion and more in general for electrification of chemical reactions. And you see here all the advantages, and this is just an example of how it works with electrification, renewable electricity, and then producing chemicals and fuels. So thank you for your attention. And this actually is a plasma that is made. Thank you.